you're interested in expanding your universe, each one of them will have something that's interesting and new.
It all takes place in the space of less than an hour.
The questions were very knowledge-based. Take the work hat off, look at something cool, and think about things in a different way.
Good morning, Suzanne. Thanks for the introduction. I'll tell you a little bit about myself. So I'm a chartered marine engineer. I've been working in the oil and gas energy sector for 10 years now, and I've always maintained a keen interest in renewable energy as well. So my background is in subsea engineering, working for engineering and project management consultancies, providing support to both operators and contractors. I joined Sealand Projects about a year ago, and my focus has broadened to include offshore renewables and the integration of marine renewables with oil and gas, with the aim of reducing carbon emissions and life cycle costs. Just briefly, a little bit about Sealand Projects. So if you don't know who we are, we're an engineering and project management consultants that work across 4 sectors: offshore, ocean energy, maritime, and ocean food. We're based in Aberdeen, but we've also got a satellite office in Glasgow that's focused on renewables. And even though our core business remains oil and gas, our ambition is to broaden our horizons to make 30% of our business from renewables in the next 5 years. And if there's any more information, you can visit our website at the bottom there. To give you an overview of what I'm going to talk about for the next 20 minutes, I'm going to just briefly give an overview of what energy transition means to me, and then take you through a number of case studies that we investigated last year as part of a project with the OGTC, and then finish by giving a little taster of some of the future works that we're currently looking at.
Okay, that's great, Lee. Thank you very much. Roger, can you like to tell us why is this concept of interest at the Decommissioning Solution Centre, please?
Thanks, Suzanne. It's an important project for us, this one, and it's a project that came through our open innovation call in the Decommissioning Solution Centre just over a year ago. Power supply is critical when you get into the decommissioning phase, and typically when we switch off the gas turbines offshore, we move on to diesel generators, and these generators use up to 5 tons of diesel per day, which of course you've got to get to the platform in the first place and then have suitable storage for the bulk quantities that you're talking about. So the project we're going to talk about today is Sealand's project, which was to develop their idea of providing renewable power to an offshore installation in the decommissioning phase. But as we went through the project, the focus has changed to the wider net zero objectives and the emissions targets of both the Scottish and the UK governments. It also fits neatly with the Smart North Sea concept that we're working on with our colleagues from the National Decommissioning Centre, which you can see behind me, which is our partnership with the University of Aberdeen.
Okay, thank you, Roger. Now, Lee, are you ready?
Yeah.
Your 20 minutes starts now.
Okay, thanks, Suzanne. So first of all, for me, what does energy transition mean to me? I'd like to just start by looking at the bigger picture slightly. For me, the energy transition is about doing everything we can to support minimizing carbon emissions and becoming carbon neutral. Essentially, this will limit the rise in global temperatures to 1.5 degrees and minimize negative impacts on our planet. I mean, you could say that the UK is a relatively low emitter of greenhouse gases on a global scale compared to the likes of China, USA, Russia, and that the steps that we take are insignificant in the grand scheme of things. However, my opinion is that over the course of history, the UK has been a consistently relatively high emitter of greenhouse gases, and it's up to us to show our pioneering spirit and lead the way in this energy transition. And this is exactly what the representatives of the UK and Scottish governments are doing. Last year, Scottish and Welsh and the UK governments were among the first to declare a climate emergency and followed this through with commitments and legislation to reduce greenhouse gas emissions to net zero by 2050 or 2045 in Scotland. Now, this sounds like a very tough ask for a nation that emits over 350 million tons of CO2 equivalent every year. But the good news is that we've already reduced our emissions by over 40% since the 1990 levels, whilst growing our GDP by up to 78%. So by being a front runner in this movement, we can become a nation, a leading nation with knowledge, skills, and technology that we can export globally. This is a strategy that's already been recognised by the Oil and Gas UK and outlined in their Roadmap 2035, and it's further highlighted by the formation of such groups such as the OGTC's Net Zero Solution Centre. So these 2 points on the left, the net zero offshore operations and integrating offshore renewables, are where I'm going to focus my presentation today. So taking a slightly closer look at the UK's oil and gas industry, the production of hydrocarbons accounts for almost 3% of the UK greenhouse gas emissions. That's over 14 million tonnes of carbon every year. And almost 3/4 of this comes from power generation. So for me, I think a good indicator is the carbon intensity, which is shown by the figure on the right-hand side. So carbon intensity is a measure of how much CO2 is emitted for every barrel of oil that's produced. The purple bubbles represent oil and the grey ones represent gas, with the size of the bubble relative to the scale of production. So what can we see from this figure? We can see that a lot of our smaller fields have a higher carbon intensity, and a lot of the bigger producers, even though they emit more CO2, they do it more efficiently with a lower carbon intensity. The average, shown by the orange bubble, for the UK continental shelf is 21,000 tonnes of CO2 per million barrels of oil. So this is higher than the European average, which is around 11,000, and even the global average at 18,000. When we compare this to our Norwegian neighbours, they produce oil at an average of 9,000 tonnes per million barrels of oil. And this excludes the recently commissioned Johan Sverdrup field, which will bring this average down even further. The red line in the graph shows the target for the UK oil and gas industry, which is to reduce our emissions to 4,000 tonnes per million barrels of oil. Okay, so this brings me nicely on to what I'm going to talk about today. So as Roger mentioned, last year, in conjunction with the OGTC Decommissioning Solution Centre and its members, Sealand studied a cross-section of major oil and gas assets within the UKCS to understand more about the power generating challenges involved in extending the life of the viable assets beyond 2035. So we explored 3 different case studies. The first investigated the immediate gains that can be achieved by increasing the operational efficiency of one's own generating plant. So this involved completing a cost-benefit analysis to interconnect 2 North Sea assets against a number of COP dates. The second study looks at providing autonomous power to the oil and gas facility by developing an adjacent offshore floating wind farm. As well as performing an assessment on the technical, environmental, and consenting, we investigated the life cycle costs of this method, allowing us to compare levelized costs with the platform current mode of operation. Third and finally, we looked at the outcomes from the autonomous power study and drew up a hypothetical scenario in which we applied a more integrated and phased approach that could provide cross-industry benefits. So starting with the first one. So here we took 2 North Sea oil platforms located approximately 10 kilometers apart. They were in the fortunate position to be rich enough in fuel gas that they could power their gas turbine and diesel generators from this. Platform 1 is a larger platform with a demand in the region of 20 to 30 megawatts and an excess generating capacity that allows it to export up to 5 megawatts of power. Platform number 2 is a smaller platform with a demand of less than 1 megawatt. This platform's also got some known HSE issues in the form of carbon monoxide emissions, which are a result of the gas turbines. So the operator here wanted us to consider the relative costs of replacing the gas turbines on the second platform with a potential opportunity to install a subsea power cable between the 2 platforms, making use of the overcapacity of the first platform and creating an islanded network. And the question is, could this be of a cost benefit? So our assessment showed that the solution could be implemented within a 2-year time period from concept to operation. And in terms of costs, we modeled 2 scenarios. On the left, scenario 1 accounts for a cessation of production of 2026, which was modeled to reflect the calculated return on investment of 5 years at a capital expenditure of 7.7 million. On the right-hand side, we looked at a second scenario which pushed production out to 2031, giving 10 years of operational field life for the cable and a cost saving over that lifetime of around 7 million. So in terms of some of the challenges and benefits of this option, so providing a seamless transition to the new power source was always going to be a challenge in minimizing the operational downtime from switching between one source to another. This option also needs a number of topside modifications, including step-up transformers and modifications to switch rooms and electrical components, which needs available deck space, which is a bit of a premium on these platforms. Additionally, there's a bit of an appetite to risk within the oil and gas industry, and it's generally thought that some sort of backup generation would be required in case there's a fault with this power cable. And there's also a challenge, legislative challenge with carbon emissions tax, in the fact that currently the smaller platform here doesn't pay carbon emission tax because it falls below the threshold. So, effectively we're producing carbon more efficiently from the first platform, but it is producing more carbon, so they're effectively going to have to pay more for their carbon tax. On the other side, the benefits are that it's a cost-effective solution from the numbers we've run, and you could get that for anything over 5 years. There's a cumulative reduction in the carbon emissions across both facilities, which leads to a lower carbon intensity across the assets. And that's partly due to the fact that you're running the generators more efficiently as well. You'll be able to resolve the CO2, the carbon monoxide issues on the second platform, and the technology to make this happen is currently available and well proven. Looking at the bigger scale, it's also a model that can be scaled to many assets in the North Sea or to more than one recipient in an island network. So the second case study that we looked at 3 North Sea assets that are around 160 kilometers from shore. Now they've got a peak power demand in the region of 40 megawatts, and they're all powered by gas turbine generation. However, in this case, the facilities are gas deficient, so they're reliant on the importation of fuel gas, which is costing them a significant 30 to 40 million pounds a year. Combined, the fields emit almost 500,000 tons of CO2 every year, and our study here investigates the potential opportunity to develop a floating offshore wind farm adjacent to the oil and gas assets, capable of powering some or all of the platform's power needs. Yeah, and we try to answer the question, can this be cost competitive? So this slide here shows a typical timeline for the development of a floating offshore wind farm based on industry data. We also engaged with the developers of some of the demonstration sites for floating offshore wind, and the feedback we got that this timeline is actually quite ambitious, and it's typically 8 to 12 years is what we're looking at. This can be down to the long regulatory consenting and approvals process that are needed, generally within the first 2 to 4 years. Okay, so first of all, I'm just going to focus on the current operating costs of the platform. So this is current operating costs using the gas turbine generators as they are at the moment. So we were able to determine a baseline levelized cost of electricity for the platforms, calculated at £157 per megawatt hour, which I've highlighted in the table there. So that's our baseline levelized cost, but we also recognize that there are key sensitivities that can cause this baseline value to fluctuate higher and lower. So these are basically, the first one is the price of gas. The spot price of gas fluctuates throughout the year, and typically operators are reliant on fuel gas, who are reliant on fuel gas pay anywhere between 1.5 to 3 times the national balancing point of gas, which is currently, or at the time of the study, was about 35 pence per therm. So the operators are paying a lot of money for their imported fuel gas. And the second aspect is the cost of carbon tax. So we completed this study based on the cap and trade scheme in line with the EU emissions trading scheme, the EU ETS, which showed a rise in carbon tax periodically. So since leaving the EU, however, we will have to develop our own legislation for how to manage carbon tax. For the moment, it's been set at a relatively low £16 per tonne for the interim period. However, with the country's drive for net zero, this is almost certain to rise, which will have a big impact on some of the larger oil and gas operators. And, you know, for comparison, when we compare this to Norway, at the moment, their carbon tax is set at €80 per tonne. Okay, so the question here is, how does our floating offshore wind development compare to our current baseline costs? So in the top right corner, I've kept the current levelized cost for the platforms as they are at the moment for a comparison. And then in the table in the middle, tried to show some of our workings. So first of all, we calculated the capex costs for the development of the 6 10 megawatt wind farm, which we worked out as roughly £350 million. We apply this to an operational timeline of either 10 or 25 years, and then we can calculate the levelized cost in a range of between 170 to 250 pounds per megawatt hour. So there's quite a large variation, and it can be contributed to the weighted average cost of capital. So essentially, this is a figure that reflects how much risk the financiers consider the development to have. The other factor is the operational time. So with a longer operational timeline, it provides a longer period to realize the benefits and bring down that levelized cost. The bottom 2 rows in the table work back from a levelized cost of £157 per megawatt hour. And the idea of this is to demonstrate the capital expenditure for the development in order for the development to be competitive. So the next slide, which I won't go through in great detail, shows a breakdown of our capex costs and identifies some of the key areas for potential cost reductions to achieve a more competitive levelized cost. So I won't go through this in great detail, and these slides will be made available after the session for you to look at these figures at your leisure. But essentially, what we've identified as the foundations and mooring systems are some of the high cost potentials that we think could be improved. Okay, so this one is just a quick slide here to show where we currently are with floating offshore wind and the ambitions of Equinor, who are on a mission to become the first developer to develop a commercial scale floating wind farm. So they're targeting a levelized cost of between 40 to 60 euros per megawatt hour by 2030, which is very ambitious. And it's actually in line with what we're currently seeing for fixed bottom offshore wind farms at the moment. So again, talking through some of the benefits and challenges of this option, the obvious benefits are the displacement of CO2. So we're talking, for this case study, around 350,000 tons of CO2 displaced every year. That's about 80% of what it's currently running at, bringing down the carbon intensity in line with net zero strategies. It also gives oil and gas operators an opportunity to expand their portfolio into the wider energy sector if they were thinking about developing into offshore wind. In the coming years, there may be potential government funding that could support these new low carbon methods. And as the technology continues to grow, this will help to drive down the cost of the development. On the other side, the challenges associated with this option, at the moment it is a high capital investment, which results in a higher than baseline levelized cost. The long timeline for development doesn't lend itself well to oil and gas, who generally need power within the next sort of 5-6 years. The approvals and consenting process between who would own the licenses, oil and gas, Crown Estate, OGA, is a bit uncertain at the moment, untested, and it's waters that will have to be passed through during the process, and it will no doubt add a little bit of time onto the whole process. And then the big one is the security of supply from an offshore wind farm. And to maintain the secure and constant supply, it's likely that generators will be required to be retained online during the operations, until perhaps such a time when battery storage or technology that presents itself can be put into the market. So our third and final case study here looks at a scenario which actually stemmed from the autonomous power study, and tries to address the challenges in providing a secure and constant power supply to the oil and gas platforms. So at the moment, this is purely hypothetical, but in this case study, we've adopted a more phased approach to align with the potential offshore wind development in the future licensing rounds. So for the purpose of this study here, we looked at the ScotWind licensing round and recognized that many of these target areas are positioned in deeper waters further from shore, aided to promote development of offshore wind. So the first phase would involve putting in a direct power cable from shore to an offshore substation and distributing this locally, as I presented in the first case study, to oil and gas assets. This cable could be AC or DC depending on the required transmission distances from shore. And there is also potential for the offshore substation to be a repurposed oil and gas platform. Second phase expands the development further into building a commercial scale floating offshore wind farm that ties back to the existing offshore substation and export cable that we've put in previously. The ownership of the cable can then be handed over to the offshore transmission owner, the OFTO, and the oil and gas platform will be provided with a power takeoff from the offshore wind farm. So this has got a number of benefits to both oil and gas and offshore wind. So the big one for the oil and gas is that they're getting a security of supply. They'll have a constant power supply from the onshore grid. Again, it'll lead itself to reducing carbon emissions and carbon intensity. The timeline is more akin to what the oil and gas industry needs. You'll have power within the next 2 to 4 years. And there's also a potential opportunity to get a return on the initial investment of the power cable if it's transferred over to the OFTO. And then finally, there's also a potential for repurposing one of the oil and gas platforms into that offshore substation. In terms of benefits to the offshore wind sector, for anyone looking to develop in this area, there's an existing export route already established that they can tap into and export power to shore, which will lead for them to accelerated development timelines, and it means they can bring production on stream earlier. So better run through, almost out of time, but just want to run through this slide very quickly to show you that a lot of you may be aware that Johan Sverdrup field came online earlier this year. So it's a huge development in the Norwegian continental shelf that is actually powered from shore by 2 high voltage DC cables. And the only thing that I really wanted to say was this project at its peak will have a carbon intensity of 670 tons of CO2 per million barrels of oil. So that's significantly lower than even the UK's target of 4,000. And then finally, moving on from these studies that we've done, we're now looking at a couple of further case studies in the North Sea, exploring the potential further from power from shore in a bit more detail, and also including a scenario for tying in a cluster of oil and gas platforms back to an existing fixed bottom offshore wind farm. We're also engaging with Round 4 and ScotWind offshore developers to explore the opportunity of a local power takeoff to oil and gas through power purchasing agreements, and also engaging with power cable suppliers who are keen to develop solutions that fit the needs of our industry, whether that be AC or DC supply. And finally, on the right-hand side, we're also taking part in a further study with the OGTC, which is, so as part of the initial study we did, we developed a digital interactive power map, which shows the location of oil and gas facilities alongside sources of marine renewable energy, such as wind, tidal, and wave. And the next step for us is to frame how this can be integrated into OGTC's National Decommissioning Centre simulator out in Newborough, which will help the industry map out scenarios for a net zero future. Thanks very much for joining, and if there's anyone's got any questions, I'll hand over to Roger, and if anyone has any questions after the session, feel free to contact myself or Graham. We're more than happy to help.
Brilliant. Thank you very much for that, Lee. Excellent presentation there. Good to see we've still got a good number of people still on the line. If I could remind you for the question and answers, if you raise your hand, I will come to you so you can ask Lee the question yourself. You can also type it, but better for interactivity if you are willing to ask Lee the question directly. So the first person who has complied with the rules is Dorothy Burke. Dorothy, I'm just going to come to you. Please ask your question.
Hi, Roger, thanks. Hi, Lee, very interesting presentation. A couple of questions. First of all, for the consenting process, if a wind turbine was inside the 500-metre zone for the platform, is it likely to reduce the time for the consenting process?
Yeah, it's a good question. I think it would probably be within, so yeah, as part of our study, we looked at a few case studies such as Beatrice and what they're doing in Norway for high wind tamping, and then also engaged with like the likes of the Crown Estate and Crown Estate Scotland, and the feedback we got is that we can't use these as a base case. Developing a floating offshore wind farm, typically you probably need to be sort of at least 2 kilometers to 2 to 5 kilometers away from the oil and gas assets. So, you know, doing something like that within the 500-metre zone is probably not considered feasible. But yeah, the second part of your question is, who would own the licenses if the oil and gas operators have already got a license to operate issued by the OGA? It's still a little bit unclear in terms of legislation and consenting. You know, would it be the OGA who issues a license to develop the wind farm, or would that have to come from the Crown Estate? At the moment, that's one of the challenges that's still a bit unclear. And yeah, going forward, we would need to seek guidance on who would drive that forward.
Great. Thank you, Lee. Can I just encourage everybody to keep the questions coming? There's a few people on the call I would normally expect that would raise their hand for a question. Graham Dallas, you're one of them. But I'm going to go on now to Steve Brown. Just give me a second, I'll unmute you. Carry on.
Hopefully you can hear me. I was wondering, Lee, if you've looked at the articulated wind column concept that ODE are promoting. It's based on a technology that was used for the mooring offloading system. And it looked to me like a good way of reducing the cost of putting the foundations in, or the equivalent of the foundations in 70 to 200 meters of water, which covers an awful lot of the North Sea, central North Sea, and even northern North Sea. Thanks very much.
Yeah, it's a good question. It's not a technology that I've explored personally, but I think yeah, like you said, it's worth investigating further, because what we identified was some of the biggest costs, particularly in floating wind, are focused around that foundations and mooring system piece. and the need for redundancy in the mooring lines and predicted failures. So yeah, it's definitely something for me to look at further.
Thank you, Steve, for that question. David Wilkinson, coming to you. Ask away.
Yeah, thanks for your presentation, Lee. I've just got a simple question. In the introduction, you mentioned marine and offshore renewables, and I just was wondering what the difference was between those two.
That was probably just. I think I was probably just caught between the two. When I talk about marine renewables and offshore renewables, I generally talk about the same thing in terms of offshore wind, offshore wave, and offshore tidal.
Okay, that's fine. Yeah, thank you.
Unless you've got a different viewpoint on that.
I just thought I was missing something, but
no, okay.
I'm happy with them being the same. Yeah.
Yeah.
Right.
Yeah.
Thanks for that, David. Dorothy, I'm coming back to you for your second question. Ask away.
So Lee, obviously there's carbon tax to sort of try and get some measure of the benefit, but when you did your cost benefit analysis, it was looking purely at the capital costs versus the return on investment, if you like. But surely if the net zero centre for OGTC wants to be successful, it'll need to have some sort of benefit number put on the reduction of carbon output. So is there some way of monetizing that in the business model?
Yeah, so for the current operating costs for the platform, we did include the costs of carbon tax as they stand at the moment, or as they stood last year before we left the EU. It's quite a fine balancing point, I think, for the UK government, because on one hand they'll want to increase the cost of carbon emissions to try and promote net zero and greener energy, but on the other hand they won't want to hinder the oil and gas industry and, you know, make it more difficult to maximize economic recovery, make it more expensive to operate, and, you know, which could effectively force oil and gas operators into an early cessation of production. So it's quite a difficult one to challenge, but I think with the state of politics at the moment, it looks as though the carbon tax is very likely to increase in the coming years.
Okay, thank you very much, Dorothy. Jenny McRae, coming to you. Please ask your question.
I think it's actually me, Roger. I'm going through, it's Jeff Haley here.
Jeff, masquerading as Jenny McRae. Carry on, Jeff.
And just using an invite that Jenny sent through. So Lee, thanks very much for a really good talk there. My question was around the three options that you've explored during this study. Were they, because they're currently the most feasible to consider at the moment and the most likely that that we're going to see in the kind of short to medium term future? And if that is the case, are there any other clean renewable energy options that you can see progressing fast enough that they might actually become contenders for these three options that we've had, based on the progress that's been made or is planned to be made?
Yeah, thanks, Jeff. Yeah, the first part, so the three options that we considered, the first one was considered almost like an easy win to export power from an overcapacity, and that was kind of progressed through a case study from one of the industry partners that we had in the study. The second one looked at more larger scale power, so sort of greater than 20-30 megawatts, and the only really feasible option for that at the moment is offshore wind. We wanted to consider that our assets in this case were further from shore, so that in deeper waters, so we had to consider a floating offshore wind farm. And then the last one was more of an idea that came about as a result of looking at the other two. In terms of additional marine renewables, so we know that for sort of smaller scale power, we've seen through the OGTC the likes of power buoys and tidal turbines that are being tested at the moment to provide smaller scale power to subsea components, and these are all extremely good as well. There is a huge potential for tidal streams, particularly in the north of Scotland. Huge opportunity there if that can be harnessed and sort of fed back into our system, perhaps not integrated with offshore oil and gas. But then on the other side, one of the big ones is power from shore. So the likes of Norway, one of the reasons that their carbon intensity is so low is because some of the fields that get power from shore, most of their onshore power is generated by hydroelectric clean electricity. So for example, if we started looking at some scenarios up in Shetland, and there's potential for the onshore wind farm and future floating offshore wind farms around Shetland, Shetland could then become a hub, to distribute power via subsea power cables to neighbouring oil and gas assets. Hope that answers your question, Jeff.
Yeah, absolutely. Thank you.
Thanks for that, Lee. Graham Dallas, I'm coming to you now. Ask away.
Thanks, Roger. Thanks for the name check and thanks for the presentation. Lee, this wasn't so much a question, it was actually just to congratulate the successful transition to the digital Tech20. I think we've all kind of been forced down this road with the current pandemic, but I think it's a big positive, all this digital interaction and communication. So well done to everyone involved.
Thanks very much.
Thanks, Graham. Much appreciated. I'm going to come to another one that's marked Jenny McRae, but I'm scared to push the button as to who it might be. I guess it might be Pamela, but here we go. Jenny McRae, please identify yourself.
Yes, it is Pamela Lamora as opposed to Jenny McRae. Roger, thank you. Thank you so much, Lee, for this fantastic presentation. Hi. So you mentioned some of the challenges around all the various approaches you're looking at, and particularly the operation time to realise the benefit. How do you think the current environment or the current COVID-19 situation and economic downturn would impact your studies going forward and the appetite from stakeholders to be engaged in the options?
Yeah, it's a difficult question to answer, given the current low price of oil and I guess the current pandemic that we find ourselves in with COVID-19. Yeah, it's hard. I mean, for what I'm seeing at the moment is that although there are sort of cuts to operator budgets, this still remains a key focus area for a lot of operators. There's pressure from government and organisations like the OGA to continue to drive this strategy forward, and I think it'll continue. Obviously, might hit a bit of a dip summer as we try and just get through this COVID-19, but I'm sure by the end of the year it'll pick up again. Okay, thank you for that. I've got a question on the chat here from Stephen Shield Lee. In your opinion, at what level will an EU ETS carbon tax start to drive offshore wind power generation for offshore assets? What is the tax sweet spot? Yeah, it's a tough question as well. As I said before, the sweet spot is hard one to answer, because you want to set it high enough that it will drive a move to cleaner energy power generation, so that the baseline, I mean, essentially what we looked at was the baseline costs of running a platform if you increase the carbon emissions, you're going to increase that baseline running costs. But at the same time, you want to provide the operators with a solution that will allow them to bring down these running costs in order to efficiently and successfully produce, especially at a lower oil price as we're seeing at the moment. So yeah, it's a tough question. It's one that is going to have to be studied a lot further than what I've done so far. Yeah, and one that will be sufficiently high enough to promote these new technologies, but not risking putting some of these older oil and gas facilities, driving them to an early COP.
Thanks, Lee. Questions seem to have dried up a little bit. No, here we go. Kevin from SDI. Question, I know you don't want to go into too much detail on the slide on the capital model, but keen to understand where the low-hanging fruit are in terms of driving down cost.
Yeah, so there's a couple of things. What we identified was, so from our background, we've got a lot of background in FPSO installations and mooring system hookups to FPSOs, and that's why we identified that the costs the industry costs for floating wind in terms of mooring systems and the foundations were incredibly high compared to what we know ourselves for FPSO mooring system hookups. The other factor is the case study that we considered is, as a smaller development. There's only 6 turbines there, producing 10 megawatts each. If you scaled that up, you would get the economies of scale, and that would help to bring down the costs. But the other thing is, if, for example, an oil and gas operator, one of the things is we assessed it on a 10-year production life. If, for example, the wind farm could be sort of disconnected, refurbished, and floated to another oil and gas facility after that, then it would help to bring these costs down even further.
Thank you, Lee. Question from Paul Slorach, who says, apologies for taking the text out, but the kids are running wild, making a racket in the background. Well, I think we all recognise that in the current climate. Has there been any consideration to building energy storage or hydrogen generation into the model to store or use any excess power? Lee?
Yeah, so I mean, we recognise that even as part of OGTC's Net Zero and the Oil and Gas UK's Roadmap 2035, building a hydrogen economy and systems and supply chain is a huge undertaking, and one that's getting a lot of attention, as well as carbon capture, usage and storage, which will obviously help towards the net zero targets. It's not something that we've studied in great detail ourselves, to be honest. More because it's not really our area of expertise, but yeah, we're fully aware that organisations such as OGTC have got a big push on building the hydrogen economy.
Great, thank you, Lee. A question from Alexei Vodopianov. Apologies if I have pronounced your name wrong. Will you use any machine learning approach or data science in integration of floating wind farms, substations and power cables?
Yeah, so I mean, in terms of what we're doing with marine science, with machine learning, so we're actually, one of the next phases of our study is to work with the OGTC at their National Decommissioning Centre out in Newborough, and looking to integrate the power map that we've already produced, which shows locations, power demand, emissions, generating capacity for oil and gas platforms in the North Sea, and then coupling that with offshore wind farms existing and future developments, and trying to show where the opportunities are for campaigning these together. In terms of the simulator in the National Decommissioning Centre, the idea is that for the benefit of the oil and gas industry, they can go there and they can plan a number of different scenarios out on the OGTC simulator and compare the things like the costs, the environmental benefits of these different options compared to what they're doing at the moment.
Thanks for the shout out on the simulator there, Lee. It's usually me that's using the simulator word, so well done. Thank you for that. Time for a couple more questions. I'm going to come to Dave Russell. Dave, ask away.
Hi, Roger. Thanks for that. And Lee, good presentation. Just a question relating more to the what I would call low demand scenarios like decommissioning. Are options currently available for that? And if the options are available, what blockers are being seen in terms of preventing those being adopted?
Yeah, it is a good question. I mean, in terms of decommissioning, as part of our wider study and the wider report we issued, we tracked the profile of a typical platform during decommissioning. Now, the one we looked at, the power demand decreased. But I do know that on certain decommissioning projects that can increase in line with each of the warm suspension, cold suspension phases of the project. In terms of technology that is available to support this at the moment, on a small scale, it depends, I guess, how much energy is required. Typically, you would still need a large enough amount of energy to sort of want to draw it from the likes of an offshore wind. I'm not sure if sort of wave energy at the moment can provide the power needs throughout decommissioning. One of the things that we looked at when we put, I mean, for example, we put a platform into a lighthouse mode, so it was very minimal power demand, and we had a very small wind turbine actually located on the platform alongside a solar panel that could provide just the very basic power needs for the platform during that lighthouse mode.
Thanks.
Excellent. Thank you for that. What was the final question there, Dave? So Lee, thanks very much for that excellent Q&A session, and thank you to everybody for the questions that come in there. I'm just going to hand back to Suzanne to wrap things up. Suzanne.
Thank you, Roger. Thank you, Lee.
Thank you.
Roger, good job of directing and facilitating. Transfer of skills into TV production. Very well done, Lee, and good Q&A and great questions from all the attendees. So you know about our next Tech20s coming up in the future. You will see a QR code on the screen, which you can scan, and it will come up showing you the Tech20 schedule. And the next one is next Friday at 11 AM. And hopefully you all enjoyed it today. As I say, this is our second virtual Tech20, and hopefully everyone's found it beneficial and found that technology can work and doesn't always feel like sometimes. So thank you, everybody. Enjoy the rest of your day, and hopefully enjoy the Easter weekend as well.